Welcome to the Deep Dive, where we cut through the noise and get straight to the insights that make you well-informed. Today, we're plunging into this invisible digital ecosystem that's pretty much all around us now, the Internet of Things, or IoT. I mean, just think about it for a second. Maybe your smart home devices, the traffic lights guiding your commute, even like healthcare devices monitoring patients or machinery in a factory. They're all constantly talking to each other, exchanging data, creating this massive interconnected web. But, here's the core challenge that comes with all this incredible growth security. We're not talking about big, robust servers here. These are often tiny devices, really resource constrained, and that makes them, well, surprisingly vulnerable, prime targets for cyber attacks.
Precisely. Yeah, the very nature of a lot of these IoT devices makes them inherently exposed. They're built with really limited resources, low memory, restricted energy, minimal processing power, which basically means they just can't run complex security software. And on top of that, they frequently ship with common weaknesses right out of the box. Things like default credentials that people just never change, or sometimes complete lack of strong encryption. It's kind of like leaving the front door wide open in a, smart city.
Okay, so given these vulnerabilities are everywhere, what's the cutting edge research looking like? How are people trying to secure these really sensitive networks? Our mission today is to unpack a really fascinating research paper that explores using a powerful deep learning technique. It's called temporal convolutional networks, or TCNs, to do just that. We're diving into a study titled Detecting Attack Behavior in IoT Networks with Network Temporal Convolutional Networks, TCNs. So we're going to explore their approach, see how they tackled it, and get into their, well, maybe surprising findings. You probably interact with IoT devices every single day without even, giving it a second thought. Maybe it's a smart thermostat adjusting your home's temperature, or sensors in your city's infrastructure managing traffic flow, monitoring air quality. Hospitals rely on them for patient monitoring. Factories use them for automation. IoT isn't just some niche tech anymore. It's really integral. It's a foundational part of our current digital age.
And that rapid, almost transformative growth, it comes with a significant flip side, those security vulnerabilities we just touched on. IoT devices are susceptible to a whole range of cyber attacks. We're talking denial of service or DOS, attacks that can just flood networks, make systems unavailable, or, serious data breaches compromising sensitive information, malware infections that can completely hijack devices. And like you said, their limited resources are a major factor, but it's also those easily exploitable weaknesses, failing to change default usernames and passwords, or the lack of robust authentication encryption that leave them so exposed.
So, yeah, when you actually stop and consider how many IoT devices you interact with daily, maybe your smart doorbell connected to systems at work, just imagine the potential impact if even a few were compromised. I mean, it could hit your personal privacy, the integrity of critical data, or even just the availability of systems you rely on for, everything from transport to healthcare. The potential consequences here are really quite staggering, aren't they? It's almost like these devices are trying to have a conversation, right? But sometimes a bad actor tries to jump in. So how do we even start listening in and figuring out who's who? The first line of defense usually is something called intrusion detection systems, or IDSs. Their basic job is just to monitor network traffic or system activities, specifically looking for malicious actions.
That's right. And traditionally, there are two main flavors. You've got signature-based IDSs. Think of those like a digital blacklist. They rely on known patterns or signatures of attacks. If they see a pattern they recognize, boom, they flag it. Then you have anomaly-based IDSs. These try to detect attacks by spotting deviations from what's considered normal behavior. But the critical limitation really is that traditional IDSs struggle big time with new or zero-day attacks. Attackers are constantly evolving their methods, finding clever ways around these established defenses. We're always sort of playing catch-up.
Right, playing catch up. And that's where machine learning, ML, came into the picture, trying to make IDS a bit smarter. ML offers algorithms that can actually learn complex patterns from huge amounts of historical data. Then they use that learning to classify network traffic as either, benign or malicious. We've seen algorithms like support vector machine, decision trees, random forest being used pretty effectively in IDSs.
Yeah, and while ML was definitely a significant step forward, even these sort of traditional ML models have their limits. A big one is their difficulty in capturing what we call temporal dependencies. Think of it like this. A simple attack might just be a single sudden spike in traffic. Easy enough. But many sophisticated attacks, things like distributed denial of service or man-in-the-middle attacks, they don't just happen in one instant. They evolve, they change, they unfold as a sequence of events over time. Traditional ML often struggles to see that whole unfolding story, missing the nuance of these time-sensitive patterns.
Okay, so if we're always playing catch up with traditional IDS and even ML struggles with these evolving time-based threats, the natural next step in this sort of defense arms race was deep learning, DL, right? This is a subfield of ML using artificial neural networks to learn even more intricate patterns. We've heard about models like deep neural networks, DNNs, convolutional neural networks, CNNs, and especially recurrent neural networks, RNNs, things like LSTM and GRU models. And they've had incredible success in other areas like image recognition, natural language processing.
Exactly. And RNNs in particular were seen as really promising for IDS because they are inherently good at handling sequential data, those temporal patterns we were just talking about. They can learn those time-dependent relationships. However, for IoT specifically, they come with some pretty significant drawbacks. RNNs can suffer from something called the vanishing gradient problem. Think of it like a memory issue. When they process really long sequences of data, like continuous IoT traffic, they can start forgetting important patterns from way back earlier in the sequence. That makes it incredibly difficult for them to learn those crucial long-term dependencies. And critically, they have high computational complexity, meaning they need a lot of processing power, a lot of memory, which makes them very hard to actually deploy effectively on those resource-constrained IoT devices.
Okay, so if even advanced deep learning like RNNs hit these very specific roadblocks, the vanishing gradients, the resource demands when you try to apply them to IoT devices, where do researchers go next? What's a more targeted solution look like?
Well, that's precisely where temporal convolutional networks, or TCNs, enter the picture. They're seen as a truly promising alternative here. These are deep learning models, yes, but they're specifically designed for time series data. They share an architecture that's kind of similar to traditional convolutional neural networks, but importantly, they've been modified to capture those crucial temporal dependencies much more efficiently.
Right, here's where it gets really interesting then. TCNs have some key advantages over RNNs that seem to make them particularly suitable for the unique challenges of IoT.
Absolutely. First off, they generally boast much faster training speeds. That's thanks to their ability to process data in parallel, which is a huge time saver when you're dealing with massive amounts of network traffic data. Second, and this is really crucial for time series data, they offer much better long-term learning. They achieve this with a clever technique called dilated convolutions. Imagine a standard camera lens seeing only what's right in front of it. A dilated convolution is kind of like a special lens that can zoom out or skip certain parts. This allows it to see patterns across a much wider span of time without needing to process every single data point sequentially, one after the other, so they can pick up on subtle, evolving attack signatures over longer periods. And finally, they tend to use less memory because they don't need to maintain that complex hidden state like RNNs do.
Okay, so it sounds like TCNs really address the specific weaknesses of RNNs for IoT. Faster training, better long-term memory, less resource hungry. But beyond just the technical advantages, what's the real-world implication here? Why is this so important for actually securing these networks?
Well, it means that IoT networks, just by their nature, involve huge amounts of time series data that needs constant monitoring, nonstop. To effectively protect them, you need models that can not only be trained quickly on this fire hose of data, but crucially, can also be deployed directly onto devices that have very limited computing resources. TCNs, with their parallel processing, their ability to spot long-term patterns, and their lower memory footprint, seem uniquely suited to meet those really demanding requirements.
So how did the researchers actually put these TCNs to the test? How did they go about detecting attacks? Was there a step-by-step process for building this IoT attack detector framework?
Right, so the first step was creating a synthetic dataset. This was necessary because, honestly, getting access to truly diverse and extensive real attack data from actual IoT networks, it's difficult, there are limitations. So they simulated attack behavior. This data set included normal network traffic, but also simulated denial of service, DevS attacks, and man-in-the-middle attacks. They built it to represent, I think it was 10 IoT devices, simulated over 7 days, collecting data 14,040 times per day, basically, every minute. And the data itself captured 5 key features, things like traffic volume, transmission frequency, the protocol being used, port number, and IP address. Then the second step was all about preparing the data. You can't just feed raw data into these models. This involved applying several pre-processing techniques to improve the data quality for the TCN model. They use standardization, for instance, which scales all the data to a common range so no single feature accidentally dominates the model's learning just because its numbers are bigger. They also used one-hot encoding. That converts categorical data, like specific protocol names, into a numerical format that machines machine learning algorithms can actually work with. And feature engineering, which is kind of about creating new, potentially more informative features from the existing ones to help the model learn more effectively. And finally, the third step was the actual TCN model construction and training. This involved designing the model's specific architecture, how its layers and connections are structured, and then fine-tuning its hyperparameters. These are basically the adjustable dials on the model, things you tweak to make it perform its best, like learning rate, batch size. The goal, ultimately, was to optimize its efficiency at classifying network traffic as either normal or attack behavior.
Gotcha. And just for those curious about the tools, what was the environment like? You mentioned the research was primarily done using Python.
Yeah, Python was the main language. They leveraged powerful libraries like scikit-learn for creating the dataset and doing that pre-processing work. And then TensorFlow, along with Keras, for actually building and training the TCN model itself. And all of this was run on Google Colab, which let them take advantage of cloud-based GPUs to speed up what can be a very computationally intensive training process.
Okay, so framework built, model trained using this synthetic data. What did the actual results tell us? Did TCNs deliver on their promise in this initial run?
Well, here's the surprising and maybe a bit sobering truth from this particular study. The model's initial efficiency in detecting cyber attacks was, frankly, incredibly low. We're talking an accuracy of about 0.49 to 0.50, which is essentially a coin toss, 50-50. It really highlights just how tough this problem is, and maybe how much work still needs to be done in this specific implementation. Because that's significantly lower than the generally accepted standard you'd want for reliable cyber attack detection, which is typically, 80% accuracy or higher.
Wow, an accuracy of zero point 0.5. That's
Oh.
basically a coin flip, like you said. I have to admit, after hearing about TCNs and their advantages, I'm genuinely surprised it was that low in this experiment. What else did they observe during the model's training? Did you have any suspicions about what was going wrong?
Yeah, beyond just the low headline accuracy number, they noted high fluctuation in the loss values during training, which basically means the model wasn't converging stably towards a good solution. Imagine trying to hit a target, but you're constantly overcorrecting your aim, back and forth. It points towards potential issues like maybe overfitting, where the model learned the training data too well, including its noise, but then struggles with new, unseen data. Or perhaps the learning rate, which dictates how big a step the model takes when it adjusts its internal workings during training, maybe that was set inappropriately. Too high, too low, preventing it from finding the optimal learning point.
Right. And could you share some of the more detailed metrics from the study, the ones that really paint the picture of these initial results and what they mean practically?
Absolutely. The raw numbers really underscore those struggles. So the accuracy was 0.4979. Precision was also low, 0.4978. But here's the really interesting part. The recall was incredibly high, almost perfect, 0.9986, which means it almost never missed an actual attack when it happened. It caught nearly everything. But the flip side, revealed by that low precision, is that it also flagged nearly all the normal traffic as suspicious, too. Imagine getting a security alert for literally every single normal interaction your smart thermostat makes. It's just not practical.
Yeah, alert fatigue would be immense.
Exactly. So that's why the combined F1 score, which tries to balance both precision and recall, was still relatively low at 0.6644. And the confusion matrix showed it clearly. Out of roughly 60,000 instances it looked at, it correctly identified only 108 true negatives, actual normal traffic. But it predicted over 60,000 positives, essentially labeling almost everything as an attack, which, as you said, isn't very helpful for real-world deployment.
No, definitely not. That sounds like a significant hurdle they ran into. So, given these initial outcomes, what did the researchers identify as the critical factors that were impacting the model's performance? What needs to change? Where do they go from here?
Well, they pointed to a few key areas, really a multifaceted approach needed for improvement. First, and this is almost always true in machine learning, data quality is paramount. This means needing more diverse, comprehensive, and probably much larger data sets, and ideally real-world data, not just synthetic. Plus, thorough cleaning, removing incorrect, duplicate, or lost data points. And scaling the data properly, like with standardization, is also crucial. Second, the model architecture itself. Selecting the right architecture for the specific data and task is vital. Things like the number of layers, the number of filters, the kernel size, the activation functions used, It all matters. And third, hyperparameter tuning. This is often a painstaking process of adjusting those crucial dials, learning rate, batch size, the type of optimizer used, and also using regularization techniques like dropout or L1L2 regularization to help prevent that overfitting problem they suspected. It's kind of like teaching a child to tell the difference between a wolf and a friendly dog. At first, they might get it wrong a lot, point at every dog and yell wolf, but with better examples, more diverse examples, and careful guidance, that's the tuning. They learn the subtle differences.
Okay, that makes sense. So what were the researchers' specific recommendations for future work then? What's the actual roadmap they laid out to make this TCN framework truly effective for securing IoT?
Right, they outlined several key suggestions moving forward. First, improving dataset quality. As I mentioned, using more complex and diverse real-world datasets is a big one. Also, significantly increasing the dataset size. And maybe employing data augmentation techniques to artificially create more varied training examples from the data they do have. Next, they advised improving the models and the hyperparameter tuning. This means experimenting with different TCN architectures, maybe adding more layers, trying different kernel sizes, and performing really detailed systematic hyperparameter tuning to squeeze the best performance out of the model. They also suggested model comparison, so actually putting the TCN model's performance head-to-head against other deep learning models often used for this, like RNNs, LSTMs, GRUs, or even standard DNNs, and maybe exploring hybrid models that combine strengths. And just for context, they noted that these other models in similar tasks often achieve much higher accuracies. RNNs around 0.75, LSTMs maybe zero point 0.8, GRUs 0.78, DNNs 0.82. So that kind of sets the benchmark, the target for where TCN improvement needs to aim.
So a clear target to shoot for.
Exactly. And crucially, they stress the need for application to real data sets. Testing the framework on actual, messy, real-world IoT data to see how it performs in a genuine environment, and testing it against a wider variety of attacks, DDoS, injection attacks, malware, and so on. And finally, a really important practical step, focusing on deployment on actual IoT devices. This involves adjusting the model specifically for those resource-constrained environments, using techniques like model compression, things like pruning or quantization to make the models smaller and faster, and ultimately developing truly lightweight TCN models that are practical for real-world use on the devices themselves.
And that brings us towards the close of this deep dive. We've explored the exploding world of the Internet of Things, its inherent security challenges, mostly due to its unique constraints. And we looked at the limitations of traditional defenses. Then we dug into the promise of deep learning, specifically these temporal convolutional networks, TCNs, and how this cutting-edge research is attempting to create smarter, more adaptive intrusion detection systems for IoT. We saw the initial struggles. Yes, that low accuracy was quite a surprise, but also the clear, detailed path forward that the researchers laid out.
Indeed. And I think while those initial results presented a significant challenge, maybe even a disappointment, they actually provide an invaluable and clear roadmap for future improvements. It really underscores that robust cybersecurity, especially in a field like IoT that's expanding so rapidly and becoming so critical, it's not really a static solution you just implement once. It's a continuous process. It requires rigorous analysis, constant refinement, and adaptation to new threats and new technologies. The journey, as they say, is really just beginning here.
It is a fascinating journey of digital defense, constantly evolving, and it leaves us with a thought. As our lives become increasingly intertwined with all these smart devices, think about the future smart devices in your own life. What kinds might rely on this kind of invisible, diligent protection, constantly learning and adapting to keep them and ultimately you safe?